Howdy folks, Mr. Reed here, and welcome to One More Question. So what I'm going to be taking a look at right now is the relationship between vertical and horizontal stretches for a radical function, but specifically a square root function. So if you want to see how these two things are related in the square root function, let's get to it. Alright, so the first thing I'm going to do is I'm actually going to write down generally g of x is equal to a f onto bx. So this is just a generalized formula for a stretch that has a vertical stretch factor of a and a horizontal stretch factor of 1 over b, so the reciprocal of b. Now, what we want to do is actually, I'm going to discuss only the square root function, so that's going to be my radical that I do here. It will be slightly different for other radical functions, but you probably, once you see this, will be able to see how it might work in another case. So, one of the things that you have to understand about radicals or square root functions is one of the ways you can separate things that are underneath of a square root. So to start that off, I'm going to actually take two perfect squares. I'm going to take 4 and 9, and I'm going to multiply them together to get 36. So the square root of 36. So square root of 36 is 6. Okay, so I'll just write that down. But I could also write the square root of 36 as being the square root of 4 times 9. So I'm just taking my 36 and turning it into 4 times 9. Now, since we know that the answer is supposed to be 6, we can come up with a way to write this differently if we weren't sure at this point yet, by realizing that if we took just the square root of 9, we'd have, it would be 3 there, and what are we going to do with the 4? Well, if we square rooted that as well, you get a 2 for that part. So you'd have 2 and 3, and if they were still multiplied together, you'd get the 6 that you were supposed to. Which means that we should be able to represent what's going on here as the square root of 4 separately, multiplied by the square root of 9. Now, this is actually something that we can generalize. So, if we were to use that generalized form and rewrite what's going on in this case right here, I was going to say f onto bx, but let's just put square root bx. So that means we can rewrite that as the square root of b times the square root of x. Now, in this form where the square root of b is outside of the base square root function, root x, right here, that is basically acting as an a value. Now, I know it's a b the way that I have it written, but it's written out in front of the square root of x, and the square root of x is kind of like our base function. It's f. So this is equal to the square root of b times f of x. So that root b is in the a position, which means that if I were to have a b, so the reciprocal of b, 1 over b being the horizontal stretch factor, that is the same as if I had selected the square root of b as the a value. So let's just kind of use a test number to show what I mean by that. So if I were to have a function where my b value was actually 4, then I could say that g of x is equal to 4x. That's actually the exact same function as if I were to separate that root 4 and from the root x, and we would end up with 2x. So an a value of 2 or a b value of 4 would do the exact same thing to this square root function. So we can see that vertical stretches and horizontal stretches actually can be equivalent, but not for the same number. And that's going to differ depending on what kind of function we're looking at. And I was actually thinking about this last night when I was trying to kind of brainstorm how I was going to talk about this particular topic. This is my first request. So someone asked if I could take a look at this particular type of thing. Now, I have mistakenly said before that this type of thing occurs for stretching because of symmetry, which is not true. What is important is actually that your bounds of the domain or range, that would be fine too, but in this case it's the domain, are unaffected by stretching. So the left bound, I'm just going to kind of draw off to the side here actually, the left bound of a square root function is at 0 for the domain. and the right bound is approaching positive infinity. So it basically covers all of the positive real numbers and also including 0. Now, if I stretch 0 horizontally, nothing happens. If I stretch infinity horizontally, nothing happens. So I actually don't lose out on any domain possibilities by stretching things horizontally. What that means is as this thing compresses or stretches out in the other direction, when it starts to get kind of, I guess you could say, closer to the y-axis, the result of that basically ends up being that you could think of it as having just been taller instead, because you're not going to lose any domain, which you do for instance, piecewise functions. If you had a piecewise function from -2 to +2, and you all of a sudden do a horizontal stretch of 1/2, this is only going to go from -1 to +1 now, which means we cannot possibly represent that with a vertical stretch instead. But for these really interesting ones, we can do that. The infinity doesn't even matter on its own. So if this thing had a domain from, for instance, 2 to infinity, that 2 would get stretched. So therefore, it would not be the same function if we were to try to represent it with a vertical stretch alone. So kind of interesting. We can, for some situations, actually create the same function, whether you're using an a value or whether you're using a b value. Since that's the case, we can show algebraically that they're the same, but it really becomes your choice. Do you want to use an a? Do you want to use a b? Really doesn't matter, because it's algebraically the same thing, and it will graphically be the same thing too. If you found that one helpful, like, subscribe, comment down below if you can think of anything that I can fix up, and as always, take care, folks.